We gave AI the power to act on its own, to browse, to run code, to duplicate itself. Which raises important questions. Can an AI agent disable its own off switch? How manageable are today's frontier agents such as ChatGPT and Claude? Can we align AI with all human values? Our guest, Aran Nayebi, proves that we cannot. It's mathematically impossible. Then, how do we build safe AI systems? We discussed it all with Aran Nayebi, an assistant professor at Carnegie Mellon University, where he runs NeuroAgents Lab at the intersection of neuroscience and AI. Welcome to Directory Conversations, where we chat with our community of AI safety researchers, share their research, collaborate, and inspire others to build safe AI systems. My name is Mary, and along with Judah, I'll be talking with Professor Aran Nayebi, an AI safety researcher at the NeuroAgents Lab. Thanks for joining us, Professor Nayebi. Before we go into the conversation, can you briefly introduce yourself and the NeuroAgents Lab?
Yeah, it's great to be here. Thank you for having me. So I'm an assistant professor here at Carnegie Mellon in the machine learning department, though I have appointments in the Neuroscience Institute as well as courtesy faculty appointment in the Robotics Institute. And the reason for kind of this cross-disciplinary appointment is because in my lab, the NeuroAgents Lab, what a neuroagent really is, it's just a term I kind of came up with in 2024, which is simply just that it's an agent that is autonomous and can explore its environment. And in doing so, by having the right signals of autonomy, its internal representations actually can predict whole brain data as well. So it can be a theory really for how natural intelligence goes and about in environments where, there isn't a well-defined external reward signal and things are intrinsically motivated and so forth. Mm-hmm. But, most of my background is actually in neuro AI, where, for the past decade, what we've been doing is showing that as you optimize neural networks on tasks, artificial neural networks, they actually end up being the best predictors of brain areas. Both across species, but also across different modalities, different areas of brain, like vision, touch, higher cortex, things like that, memory. And as AI kind of became more capable, it became important to start to take seriously the safety question because, now you had an artifact. So initially, right, like, it was in vision, you just had CNNs, right? That's kind of one of the first modern successes of deep learning at scale on ImageNet was CNNs. And actually those turned out to be the best theories we have currently of visual cortex 2 in the primate. They best predict response patterns there too. But then as we kind of built more and more of these systems, now they're starting to become agentic and things like that. I think that's where the safety comes in a role, where we want to have guardrails on top of these autonomous agents that we're building if they're going to be deployed in the open world.
Mm-hmm. Okay, I see. Thank you. Yeah, so you have mentioned how the research you are doing connects to AI safety, right? Okay. So if we go into your less wrong article, from barriers to alignment to the first formal corrigibility guarantee, you write about factors that make it hard to build AI systems that align with all human values, as well as the safety targets that are also feasible. Could you elaborate on modeling alignment as a communication problem and your recommended setup for such a framework?
Absolutely, yeah. So the idea there was that basically in a lot of these settings that people were looking at, like things like AI safety via debate, where you have Alice and Bob and they're trying to convince a human judge who is correct versus the other person who's lying versus telling the truth, as well as the very early frameworks of in alignment from Dylan Hadfield-Manel. So like SERL, so cooperative inverse reinforcement learning, where a human and a robot are trying to complete a task, and the human knows what the reward function is, and the robot is trying to collaborate with the human to complete the task together. All of those kind of seem like special cases of a broader kind of general communication problem between agents. So in other words, you had n agents. It didn't have to be 2. It could be 3. It could be 4. It could be as many as you wanted. There had to be more than one. And they were just trying to come to agreement, basically, about some objective, some reward function, or some set of specified values, whatever they might be, which are bounded in some range. And the issue, though, is that, okay, so that's interesting, but how do you formalize that? And in the game theory literature, there was a very famous theorem from 1976, about 50 years ago, by Robert Aumann, who is actually a Nobel Prize-winning game theorist, known for studying equilibria in repeated games. He didn't get a Nobel Prize for this work, but it's very influential work, because what it says is essentially that if Alice and Bob, he just considered two agents, are rational, and they start from the same prior, meaning that they went to the same school, they have the same kind of training. And if each one knows the evidence that they're presenting, so they know each other's posteriors more formally, then they can't agree to disagree. So in other words, they have to agree. And so that's interesting, because it starts to formalize what agreement means and when agreement happens. Now, the problem, of course, is that in the real world, you can't assume that an agent and you or anything else has a common prior with you. Like, they don't come from the same place. They've trained on different data. There's some overlap, but it's not 100%, right? And furthermore, we often want to study, it's an iterative process, right? We communicate, there's messages, information gets revealed, and then we update, right? And so what you want to capture then is, and it's not always that you get exact agreement, it's often approximate and probabilistic and things like that. So there's iterative updating, there's a finite resource of messages being exchanged, bits being exchanged, and then you don't always have a common prior. And so what I did was, kind of relax all those original assumptions of the Aumann agreement theorem, and then what I could show, what I was looking for were hardnesses. So in other words, I wanted to, hardnesses in the settings where you could prove this kind of alignment. So in other words, it's not easy, but you can show that, of course, in this kind of cooperative setting, they're going to align eventually, and you can bound the number of resources they need. But I wasn't looking for an upper bound, I was looking for a lower bound. In other words, I wanted to study settings where it was hard and you needed at least as many resources to do things. Because if you identify hardnesses in the best case scenarios, then you can learn to avoid those hardnesses by identifying them in practice where you don't often have those guarantees. And so one of those was that even if you're computationally unbounded, if you have too many objectives or values you want to align over or agree over, there are settings where you need at least as many bits of information as the number of objectives. So if those objectives are very large, so for example, you and I might agree on some subset of our state space, some subset of things that we agree on, and then disagree on others. So we need a different objective for that set of things. So in the worst case, you can imagine, if you're trying to align all human values, that really across all humans, you have one objective per state. And the number of states is exponentially large, so that really starts to become an intractability. So aligning to all human values, you can prove is not a tractable target. And in fact, this was the idea of aligning a full value alignment was actually originally with the coherent extrapolative volition idea, like you can project out all human values and then have the friendly AI aligned to those. So, but that's just not going to be computationally feasible. So I think that's interesting. And also this setting, even though it's hard in the cooperative setting, I think the cooperative setting is actually also telling, even if it wasn't hard, because oftentimes we instruction tune these agents, so they're following our instructions anyway. So it's actually a reasonably not terrible setting, but really the main thing is to show that even in these really best case scenarios, things are hard. And one of these is full value alignment. The other one is reward hacking. So people talk a lot about reward hacking. And so if you restrict yourself to broad kind of natural communication protocols, like ways in which agents could communicate that involve finite numbers of bits and things like that. So rather than all possible communication protocols, which is what this full value alignment intractability was about, then you can also show that there doesn't exist a globally unhackable reward function. If you have some kind of bounded functional and you're resource limited, there exist settings where you need at least as many bits of information as the size of the state space, even if you're computationally unbounded. So what that means is that if you're a computationally bounded agent and your state space is big, which is really the setting we're in often, then you can't guarantee alignment across the whole state space. So you have to pick slices of the state space to align over. So what's the implication of the other thing? The other thing is try to identify a small set. Either you have a small set of values per setting. Like for a coding agent, maybe it's you don't have to solve human ethics, but you can you just tell it to write functional code, clear code, concise code, well-documented code. Okay. But maybe additionally, you could also have a small set of values that are universal that we can all agree on, like corrigibility or avoiding loss of control. And so that was kind of what led me to corrigibility, was realizing that that maybe that was a reasonable target that could be specified as a small number of values that's universal. Because I think we can all agree that, at least in the AI safety community, that having the AIs take over is maybe not the best scenario. And so that's something to keep in mind there. And then in the reward hacking case, it's really a focus on slices of the state space that are safety critical rather than the whole state space.
Okay, thank you. And just to make it more easier to digest, this conclusion that aligning AI to all human values is near impossible. Could you just say what does it mean for the real world?
Yeah. So what it means for the real world is that actually what we want to do when we want to build agents to align things is we have to come to consensus as a community as to what kind of small set of values we want the agents to have and possess as they go out in the real world. I think one of those should be loss of control, and I can show with corrigibility, for example, that single reward functions like RLHF won't give you that guarantee of trading off between safety and performance when the time comes and the two conflict. But what you can prove is that avoiding loss of control can be specified in a few objectives, like not taking irreversible actions, remaining editable, waiting for the human, things like that. And those kind of sit higher priority over the task reward. And so that's how you can prove a guarantee. And so that ends up coming out to 5 values, including the task reward. And so that's the kind of implication, is that that's what we should be building towards, and that we can build it. And we can build safety features that have theoretical assurances.
Okay, yeah, understood.
What we want is a science of safety, ultimately with guarantees.
Understood.
Just the way with airplanes. Yeah.
Thank you. Understood. Yeah, I think it's really interesting finding, because I thought many would want AI to align with all human values, but we realized that, actually it's impossible. Okay, and Chudo, I can hand over to you to ask questions.
Yeah, thanks, Miriam. Thanks, Prof. Nayebi. Still on the Less Wrong article, but diving into what you just talked about, corrigibility and safety targets that are manageable. Could you, go into corrigibility a bit and why that is manageable? You've touched on that, but if you could elaborate on that a bit more. And then in that article, you talk about the lexicographic approach. You kind of talked about it just now, like the priorities, right? If you could elaborate on that and why you recommend that approach. How would that help to build safe AI? And then lastly, if AI agents and sub-agents in everyday applications could violate that lexicographic approach you recommend in the article.
Yeah, it's a great question. So the way I came across corrigibility was after I had even the first barrier of aligning to all human values. I was reading the 2015 article of Nate Soares and Kalski and these other folks from MIRI that was published, I think, in AAAI, one of the AAAI workshops, and on AI ethics. And they had proposed this idea of corrigibility. It wasn't proven. It was an informal idea of maybe what we want out of a safe AI. And I thought it was remarkably lucid and very clear as a target, because it just seemed so correct. Basically, right? Because the thesis they make in their later book of if anyone builds it, everybody dies, is that you only get one shot at building superintelligence, and if it does something bad, it's hard to reverse it and edit it. And what corrigibility fundamentally does is it keeps those agents editable, and so that if you, and they defer to humans and things like that. so that if you feel like, okay, you want to go back and revisit other values in the agent, not just the corrigibility, but other things you might put in there, you could do so safely, right? And it sort of, allows you to have as many tries as you want. And that holds with sub-agents that are successor agents that this agent could build. And so what was interesting in their article is, even though they didn't have a theorem or any proofs for what was the solution for corrigibility, that was an open question, they showed how a lot of single utility proposals, single reward function proposals, failed to satisfy corrigibility. And I thought that was remarkably insightful to kind of think through. And that led me actually to the way I first thought about it was, okay, let me try to prove that a single utility is not enough in general. And so I could show that in the paper that you just don't, basically it comes down to like a paperclip maximizer argument. Like, you don't have a guarantee that if task performance is what you're optimizing for, that would trade off with retaining corrigibility if your task performance is a higher reward. And so kind of like if you were to count paperclips and you want to maximize those, and it was more advantageous therefore to take over the world and turn all the factories into paperclip, kind of that same kind of thinking. And then I was already thinking about multiple objectives because of the intrinsic barriers work already. And it kind of seemed natural that, corrigibility, just the way it's phrased, would kind of come down to multiple objectives rather than one. Like, what you sum them all up, but you still have constraints as to like, this one is higher than this one, and this one is higher than this one, and they all are higher than the task reward, and the task reward is bounded. And so that was the basic kind of approach there. And that's why lexicography seemed like a natural construction, because what you can show is that if you have sufficiently large enough weight gaps between the different desired data of corrigibility, you could prove that not only in the single step partially observed off switch gain, but also the multi-step, like repeated interactions, you can prove that it's the optimal policy is corrigible. And then furthermore, you can kind of take a machine learning point of view and say, look, what if I estimate these utilities and I have some kind of bounded error on estimating them? Then you can also show that the total probability of a failure is also bounded. And so what that means is that you now, in practice, you're not going to get 100% corrigibility all the time. In practice, you're going to learn these utilities. And so what you're going to do is you want to know, if you know what the failure probability is, that's very powerful, because you can tell, okay, is this acceptable or not ahead of time by computing it in a lot of ways. And you can monitor how well you're learning those utilities on held out sets. So in other words, you've reduced the broader alignment problem into a machine learning problem, which is great because machine learning is tractable and we can do it well, and we can track the error, the amount of error, and policy we can then be used in conjunction to determine whether that's sensible or not. And then the other aspect of it is like you do want to entrain these utilities, because what happens there is that if you don't entrain the utilities, you can imagine putting these in a safety filter. And one thing I asked myself was, does there exist a perfect safety filter? In other words, like if I handed you an agent in an environment, could it determine whether some kind of catastrophe would occur? Mm-hmm. And you can actually prove a no-go result there too, where you can show that in general, unless you restrict the class of agents, in other words, by training utilities into them, or you restrict the environments or like the evaluations, you can't prove in full generality, you can't have a perfect safety filter, because that's actually equivalent to an idea in computer science known as the halting problem. So if you could do that, you could actually predict whether any arbitrary program would stop on its inputs or not, e.g. detect catastrophe or not, and that's not, that's undecidable. You don't have such a thing. And so it would be a contradiction to that. So there's limits to safety filters, and so really the best way is either, red teaming evals that are on some bounded horizon, and or entrain those utilities into the agent so you have some guarantees there with the failure probabilities.
Great, thanks. Just to stay on the topic of corrigibility, but this time shifting to another material, which in this case is the research paper you published, Rogue, Misaligned Agent Behavior Arising from Ordinary Computer Use. You assess misalignment behavior in AI agents and sub-agents in non-adversarial settings, and you introduce a benchmark to evaluate their corrigibility. could you shed more light on the research, that rogue research, and the real life implications of that finding? And how can the rogue benchmark you introduced be used to build safe AI?
Good question. So, so Rogue was something that was spearheaded also with in conjunction with my student, Jeremy Tian, my PhD student, who's co-advised with Zico Culture here at CMU. And what we were curious about was to understand to what extent are current frontier agents incorrigible. So in other words, the thing with RLHF is that no one person in these companies knows all the data that goes into fine-tuning or to safety pre-training RLHF. You kind of focus on your set of data sets and you put it in a big pot and then you see what comes out. It's a very complex data pipeline. And so because there's no guarantees there, we were just kind of curious, like to what extent, how effective, how corrigible are you, how much are you getting corrigibility already in practice in a lot of settings without, I don't know, like rethinking things. Just with standard RLHF or RLAIF, which is like Anthropic's models used where you have an AI judge. We found that actually in the text setting, like if you had it put in these settings of like, being able to override the human or disable an off switch and you're just chatting in a chat window, across these different models, they're actually like really quite well aligned. They weren't really doing bad things and they were pretty extensively fine-tuned in that regard and did a great job in a lot of cases. I mean, there's some misalignment. It wasn't perfect, but it was honestly acceptable in a lot of ways. What was interesting though was to then, because again, we build agents and so we care about embodying them and things like that. And so we put them in a computer use environment. And again, we weren't looking at jailbreaking. Like I think jailbreaking is good for security reasons, but I'm not interested in security. And like, I think a lot of people have already done a lot of great work there that, contributing to jailbreaking is not really, it's very saturated anyway. And it's, but I was just curious, like in general, like, I don't know, like say you put them in a computer use environment and you have some shutdown button and it can rewire it, will it, right? If you take those exact same scenarios we put in text and put them in the computer, will safety violations happen? And we found, oh yeah, it did, and a lot. And not just one model, but so many. And so it wasn't like contrived scenarios where we're goading the agent to do bad things. We're just, naturally letting it complete tasks, spawn sub-agents, things like that. And we would see with access restricted resources, access off switches, things like that, in order to kind of complete its tasks and things. So even though it had options to not do those things, to be able to finish those tasks, it still did those things. And so the implication then for safety research is that actually now you have a way to evaluate corrigibility because you really have a corrigibility measure from Rogue in real settings, like not just some game, but in a real setting, in the settings that people are increasingly using these agents for. And as far as we can tell, we were also the first benchmark to use and evaluate sub-agents because that was just a new capability that came out. And the reason I thought of using sub-agents was really because of incorrigibility. You also wanted to be corrigible with respect to sub-agents. So that was actually something that was in the original Soares et al. 2015 paper. And we wanted to kind of test that aspect too, especially as sub-agents are becoming more and more prevalent to be able to finish a bunch of tasks that it can spawn.
I'm just curious, like, so now if the Rogue benchmark could help, check for like corrigibility in these benign settings, would the success of a model being corrigible in benign settings, would that have consequences for it in adversarial settings? Does that mean that if it's good in benign settings, would it be also corrigible in, other non-benign settings? Do you think?
No, I think that's right. I don't think there's a guarantee there. In fact, actually, the intrinsic barriers paper because of that barrier of reward hacking is inevitable. It actually suggests that you want to be, when you're selecting portions of the state space to have your alignment over rather than the whole state space, you actually want encouraging multi-turn interaction, not just single shot like RLHF, but multi-turn interactions that are teasing out adversarial things. So I think in practice, we want to stress test things. Absolutely, we want to include the adversarial stuff too. And so if you're going to build and evaluate a corrigible agent in fullness, you'd include the adversarial stuff. We were just curious in Rogue, just like, to try to move towards more natural settings that were a bit less contrived, just to see is it a natural thing that gets elicited in just doing tasks? And that was really the main reason. But I think you're right. I think in fact, very well supported by the theory, you also want to include the adversarial stuff, absolutely, because you want to test the degree to which you have this kind of alignment on the portions of safety critical state space slices.
Great. Thanks. So this brings us to like future research directions you think that work could go, both the Google benchmark work and the corrigibility research in general. Are there future directions, pointers for those interested in progressing this area of study that you could point to?
I think kind of building out corrigibility at scale is definitely of interest to us. And partnering with people to do that will be important. Who have a lot more resources and resources to do it. I think we can prototype some stuff, and we're working on that now. But I think the other aspect of it is that like it's also figure out what other values you want to have, right? So I kind of think of corrigibility. So like I mentioned, right, like the nice thing about this corrigible design, this lexicographic, is that it sits on top of the task reward, so that like whatever safety fine-tuning people have done, the great work that they do in companies to get the RLHF reward to be reasonable, you don't have to like overwrite that. You just can use it, and then as an external safety filter, just to have some kind of cheapness, you can kind of already have something that overrides the actions that this RLHF thing misses. So you can kind of have the best of both worlds. Which I think is great. Of course, again, supported by the theory, you want to post-train. You want to have this kind of corrigibility as part of the post-training pipeline, not just as an external safety filter, because safety filters have these fundamental limitations, but they're really convenient. And so I don't see them, despite their lack of theoretical robustness in fullness, I think they're a really valuable source of practical safety guardrails, and exploring that and putting that around agents is going to be important. Now, the other question is given that we can't do full value alignment, what other things do we want to put? So, like in other words, you can imagine corrigibility sitting at the top, like avoiding loss of control is like the most highest priority thing, and then something in the middle is like other values you might want to have, or even as looped into part of the RLHF training, right? Like depending on the application, maybe you want for an elder care AI, you maybe want it to actually encourage it to not be so appealing to talk to, but really actually to encourage the human user to go and talk to other humans, right? That's an interesting question. Like, how do we build more anthropically beneficial agents beyond avoiding loss of control? Like, let's assume that that's a given now that we have that. But like, how can we, have other things that like have implications for meaningful implications, for positive implications for human psychology when they interact with these agents? I think, when like, for example, like phones have probably been very detrimental to our psychology because like fundamentally, I think we're wired in a way to like want in-person face-to-face interactions in real time, and texts kind of remove that. They remove the personhood there. And so I think we have to think critically, like when we build these agents, to not necessarily have it be a hyperphone that's even more interesting, but probably to encourage more human connection. And how to do that, I think, is an interesting open question. And it could fit into that lexicographic design quite naturally, where you have loss of control, some anthropically beneficial values, and maybe that's over RLHF even, or as part of it.
Great. Thank you so much. I'll pass it back to Mirin for follow-up questions.
Where can we learn more about NeuroAgents Lab and your research?
So if you go to my website, cs.cmu.edu/Nayebi, you can read all about it. And in fact, I have if you go under our research tab, I have like a lab plan that kind of talks about the projects in general at a high level, like what a neuroagent is, and like what are the core components of it, and things like that. And trying to ultimately work towards really a science of intelligence. So in other words, you engineer things as artifacts of intelligence, but trying to study how their societal implications, but also their scientific implications is really what we're after here. So it kind of works downstream of engineering, though we do engineer our agents too. Yeah.
Very interesting. So are there any upcoming publications coming soon?
Yeah, definitely. Like I mentioned, we kind of want to stress test and see how Rogue can help us build more corrigible agents. That's something we're looking to do. And we also have some work in, like I said, we put agents in bodies, and so we have some work also on tactile sensing in robots. That's more about just getting them to be safe in the sense of capability. That by having feedback and touching objects, they can do more dexterous tasks like lifting cups and things like that. And so that's a kind of critical for the next generation of building one of the first large-scale simulators that can simulate so many different tactile sensor types to help design the next generation robot hand. In fact, we find that certain types of sensors, like proximity sensors, are really great and more effective than other types. We even have temperature sensors, so one of the first to have that in a physics simulator. And we show that having kind of mirroring the human hand in the sense of having touch sensors throughout the whole hand is better for tasks than just in the fingertips, which is how current robot hands are designed. So anyway, I'll just say we have kind of different pipelines in both neuroscience and AI. I mean, we built a virtual zebrafish. I don't know if you saw that, but we had
really? That's cool.
Predicted whole brain data. Yeah. So trying to figure out good curiosity signals. So what are good signals of autonomy? Oftentimes we've been finding that tracking the progress in a world model is aligned with better behavior in sim, but also in animal behavior too. And so we're basically trying to figure out what are good curiosity, interesting motivation signals, and then the safety kind of is the layer on top, the control layer on top that is has higher priority over those. That's kind of the goal. Yeah, and then embodying it, and so that's where the hands come in.
Okay, thank you. Thanks for joining us today, and we look for future conversations with you and your team. Thanks for sharing your research. And that's it for today. Okay.
Thanks, Prof. Nayebi.
Hey, thanks so much for having me. This is great.
That's it for today's episode of Directory Conversations. If you are an AI safety researcher and would like to join our community or chat with us on an upcoming episode, contact us at aisafetyresearchdirectory@gmail.com. Bye, until next time.